Right now, Earth is traveling through space at roughly 1.5 million miles per hour. Not in any direction you chose, and not at any speed you can feel. You have never experienced this motion. You never will. But it is real, confirmed by multiple independent measurements across decades of observation, and it points toward a specific region of the sky, where something enormous is pulling an entire collection of galaxies in a single coherent direction. The fact that we did not know this was happening until the latter half of the 20th century says something important about how hard it is to map forces operating at cosmological scales. The story of how scientists uncovered this motion, identified its causes, and discovered that our understanding of the universe still has some significant gaps in it is one of the more intellectually satisfying stories in modern science. Start with the numbers, because the numbers themselves are worth sitting with. Earth orbits the Sun once per year along a path roughly 600 million miles in circumference. To complete that orbit on schedule, Earth must move at approximately 67,000 miles per hour relative to the Sun at the center of our solar system. That speed is continuous. It does not slow down or speed up in any meaningful way. You do not feel it because the atmosphere, the oceans, and everything else around you is moving at exactly the same velocity in the same direction. The sensation of motion requires a reference point that is behaving differently from you. Inside this planetary system, everything moves together. That is the first layer of motion. The second layer is larger by a factor of roughly 7. Our entire solar system also orbits the center of the Milky Way galaxy. This orbit takes approximately 225 million years to complete. The last time our solar system occupied this same position in its galactic orbit, the earliest ancestors of dinosaurs were just beginning to appear on Earth. To maintain this orbit at the scale required, our solar system travels at approximately 500,000 miles per hour relative to the galactic center. Still no sensation of movement. Still no felt experience of any of this. The third layer is where the story becomes genuinely strange. The Milky Way galaxy is not standing still either. Neither is our neighboring galaxy Andromeda, or the Triangulum galaxy, or the roughly 50 smaller satellite galaxies that together form a gravitationally connected cluster called the local group. The entire local group is in motion, and that motion was measured using something remarkable as a reference point. Roughly 380,000 years after the universe began, the temperature of space dropped below the threshold needed for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was opaque. Photons could not travel freely because they kept colliding with free electrons scattered throughout the hot, dense plasma that filled all of space. When neutral atoms formed, the universe became transparent for the first time. Light was suddenly free to travel in all directions simultaneously. That light has been traveling ever since. As the universe expanded, those photons stretched to longer and longer wavelengths, eventually becoming microwaves. Today they fill the entire sky uniformly from every direction at once, arriving at Earth from a sphere 13.8 billion years in radius. This is the cosmic microwave background, and physicists detected it by accident in 1965. Two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing an antenna originally designed for satellite communications. They noticed a faint, persistent noise arriving equally from every direction. They checked the equipment. They cleaned the antenna. They removed pigeons nesting inside the receiver. The noise remained. When they eventually described the problem to cosmologists, the explanation came back immediately. What they were hearing was the thermal remnant of the Big Bang itself, arriving from every point in the sky simultaneously. Penzias and Wilson received the Nobel Prize in Physics in 1978. The cosmic microwave background arrives at a temperature of approximately 2.7 degrees above absolute zero. When it was first detected, the picture seemed smooth, essentially the same faint warmth from every direction. More sensitive measurements through the 1970s revealed something subtle but profound. The temperature was not quite identical in every direction. One half of the sky was microscopically warmer. The opposite half was microscopically cooler. The temperature difference was approximately 1 part in 1,000. Physicists call this the temperature dipole, and it is a direct fingerprint of motion. Here is the physics. When you move through a medium that fills all of space, the waves in front of you get compressed, and the waves behind you get stretched. Move toward a sound source and its pitch rises. Move away and the pitch drops. The same principle applies to the cosmic microwave background. A moving observer should see the background slightly blue shifted, meaning slightly hotter, in the direction of travel, and slightly red shifted, meaning slightly cooler, in the opposite direction. The cosmic microwave background dipole measured exactly that pattern. From the size of the temperature difference and its direction on the sky, physicists extracted a speed and a bearing. The local group, our collection of roughly 50 to 60 galaxies, is moving at approximately 630 kilometers per second relative to the rest frame defined by the cosmic microwave background. In more intuitive terms, that is roughly 1.5 million miles per hour aimed at a specific point in the southern sky, near the constellation Centaurus. To be precise about what this means, the cosmic microwave background fills all of space. It defines, as close as anything can, a reference frame for the universe as a whole. Our velocity relative to it is not caused by local expansion. It is a genuine peculiar velocity, real physical motion towards something. The dipole confirmed the motion with precision. What it could not do was identify the cause. Something was generating this flow. The dipole measured the speed and direction and went silent on every question about the source. It was like measuring the depth and bearing of an enormous set of tracks without being able to see what made them. Following those tracks back to their source would take another decade of work, a new measurement technique, and 7 researchers willing to stake significant professional reputations on a finding their colleagues initially found implausible. In 1980, 7 astronomers began an ambitious observational project. Their names were Sandra Faber, Alan Dressler, Donald Lynden Bell, David Burstein, Roger Davies, Roberto Turlevich, and Gary Wegner. They became known later as the Seven Samurai, a nickname attached by colleagues who found their ambition both admirable and alarming. The concept was straightforward. The execution was grueling. They wanted to measure the actual physical velocities of galaxies moving through space. Their peculiar velocities, the motions that were not just a product of the universe expanding. To isolate peculiar velocity, you need independent distance measurements. You observe a galaxy's recession speed. You subtract the expected expansion of the universe for that distance. What remains is the peculiar velocity, the real motion through the gravitational landscape. The challenge is getting precise independent distance measurements for hundreds of galaxies without relying on any assumptions about expansion itself. The Seven Samurai developed and validated a technique called the dn sigma method. Elliptical galaxies, which are large, roughly football-shaped galaxies scattered throughout the cosmos, have a measurable internal property called velocity dispersion. The spread of stellar orbital velocities inside an elliptical galaxy correlates tightly with that galaxy's true physical brightness and size. Measure the dispersion, calculate the true brightness, compare it to the galaxy's apparent brightness as seen from Earth, and the distance falls out directly from the comparison. No assumptions about expansion required. An independent ruler built from the internal physics of the galaxies themselves. Over years of telescope observations, the team measured hundreds of elliptical galaxies across a wide region of the local universe. What they found stopped them. Every galaxy had a peculiar velocity. That was expected. What was not expected was what happened when those velocities were mapped together. They were not pointing in scattered independent directions. The galaxies were flowing together in a coherent, organized stream. Hundreds of galaxies spread across a region hundreds of millions of light years across, all moving toward the same point in the southern sky, at speeds ranging from 600 to 700 kilometers per second. They published in 1986. Their conclusion: something enormous sat in the direction of that flow, a massive concentration of matter generating the gravitational pull behind those coordinated velocities. They called it the Great Attractor. The scientific community was not immediately convinced. The problem was structural. The standard cosmological framework assumed the universe at large enough scales was smooth, matter distributed roughly evenly. No single structure large enough to dominate an entire region of the sky. The models predicted peculiar velocities would be modest, local, and independent of each other. What the Seven Samurai were claiming was that a vast region of the universe was gravitationally organized around a single dominant source. This was outside what the models predicted. Colleagues raised methodological objections. The dn sigma technique was relatively new at the time. Perhaps there were systematic errors in the calibration. Perhaps the sample was biased. Perhaps the flow was real but smaller than reported. Some of those objections were scientifically fair, but the data held across every challenge to its core. Hundreds of galaxies pointed the same direction, and that direction aimed straight into a region of sky where direct observation was essentially impossible. There is a band across the entire sky that optical astronomers cannot effectively use. It follows the plane of our own galaxy, running in a wide stripe that at its thickest covers tens of degrees of sky. Astronomers call it the zone of avoidance. Behind it sits roughly 20% of the observable universe, hidden from ground-based and space-based optical telescopes alike. The reason is dust. The Milky Way is a flat disk of stars, gas, and dust hundreds of thousands of light years across. We live near the outer edge of that disk. When we look toward the galactic plane, we look through the thickest portion of it. The dust in that plane absorbs and scatters visible light with extraordinary efficiency. Galaxies that would be bright and easily observable from other viewing angles simply disappear behind it. The Great Attractor sits almost exactly inside that strip, the point in the southern sky where hundreds of galaxies were converging. The gravitational target the Seven Samurai had identified from years of careful measurements fell almost precisely behind the densest portion of our own galaxy's dust plane. The answer to one of cosmology's central questions was hidden behind the one obstacle that the most powerful optical telescopes could not penetrate. Picture what that meant for a researcher in the late 1980s. You have the velocity data. You have confirmed the flow across hundreds of independent galaxies. You know approximately where to look. You apply for telescope time, wait months, point the best available instruments at that region of sky. You see nothing useful. The dust swallows everything. The Great Attractor, if it existed as the Seven Samurai described, was sitting behind a wall that visible light could not cross. The only approach was indirect. Astronomers worked around the edges of the zone of avoidance, sampling regions just above and below the galactic plane, trying to extrapolate inward. It helped somewhat. It was not enough. Without direct observation, mass estimates for the Great Attractor relied entirely on the velocity patterns in the surrounding galaxies. Different assumptions fed into those estimates produced wildly different results. Some estimates were reasonable, some were staggeringly large. Without seeing the structure itself, there was no way to anchor the calculation. Seeing through the dust required leaving visible wavelengths behind entirely. X-ray photons carry far higher energies than visible light photons. The dust grains that absorb visible wavelengths have almost no effect on X-rays passing through them. If a massive cluster of galaxies sat behind the zone of avoidance, the superheated gas trapped within that cluster would radiate X-rays, and those X-rays would travel through the galactic dust essentially unimpeded. ROSAT, the Röntgen satellite, launched by Germany in 1990, provided the first true all-sky X-ray survey. It orbited Earth for 9 years and built an image of the entire sky at X-ray wavelengths. When researchers examined that image toward the galactic plane, they found galaxy clusters that optical surveys had never detected. A follow-up program called CESA, the Clusters in the Zone of Avoidance Survey, extended this work systematically. By the early 2000s, it had cataloged more than 200 galaxy clusters hidden behind the galactic dust, invisible in ordinary light, glowing in X-rays. Near the center of the Great Attractor region, one cluster stood out from all the others. The Norma cluster, cataloged as ACO 3627, sits about 220 million light-years away, directly behind the galactic plane. X-ray observations revealed it to be genuinely massive. Its total mass came in at roughly 10 to the power of 15 solar masses. For a galaxy cluster, that is a large number. For a moment, it seemed like the answer. The Great Attractor had been described as a single dominant object behind the zone of avoidance. Norma was a dominant object behind the zone of avoidance. Many researchers assumed Norma was the Great Attractor, or at least its core. Then they ran the numbers. Norma's mass, while substantial, was not nearly large enough to account for the observed velocities. The gravitational pull from a cluster of 10 to the power of 15 solar masses at that distance generates a specific and calculable flow. That flow was smaller than what multiple surveys had measured. Norma could explain part of our motion. It could not explain all of it. The original picture required revision. The Great Attractor was not a single massive object. It was a gravitational basin, a broad region where matter had concentrated more heavily than average, and Norma was the largest known node within that basin. The thing people had been imagining as one monstrous concentrated structure resolved under X-ray observation into a collection of moderately large structures spread across a gravitationally overdense region. This raised a harder question. If Norma and the broader Great Attractor basin together could not fully explain our observed velocity, something else had to be contributing. Something farther away. Something that had been considered too distant to matter. That something had a name. In 1930, a British-American astronomer named Harlow Shapley cataloged an unusual concentration of galaxies in the constellation Centaurus. It was distant enough that for decades most cosmologists filed it as a curiosity. A large cluster far outside the local cosmic neighborhood, probably not relevant to local gravitational dynamics. They were wrong by a significant margin. The Shapley supercluster sits approximately 650 million light-years from Earth. That is roughly 4 times farther away than the Great Attractor region. In cosmology, distance typically implies diminishing relevance. Gravitational influence falls off with the square of distance. something 4 times farther away, exerts 16 times less gravitational pull at a given mass. For Shapley to matter to local dynamics, it would need to be extraordinarily massive. It is extraordinarily massive. The Shapley supercluster contains more than 8,000 individual galaxies. Its total mass runs to approximately 50 quadrillion times the mass of our Sun. It stands as one of the largest gravitationally concentrated structures within several billion light-years of Earth. For most of the late 20th century, the assumption was straightforward. Shapley was too far away to contribute meaningfully to the motion of the local group. The Great Attractor region was the dominant gravitational influence. Shapley was background. Mid-2000s surveys began dismantling that assumption. Researchers tracing the precise motion vector of the local group found that the flow did not stop at the Great Attractor. If the Great Attractor were the sole explanation, the velocity vector would point directly toward its center, and the surrounding galaxy flow would converge there in a matching pattern. Instead, the velocity field continued past the Great Attractor, pointing farther in the direction of Shapley. Multiple independent analyses confirmed this result. The motion of the local group, when compared carefully to the gravitational landscapes of both structures, showed contributions from both. Shapley, despite its enormous distance, was adding to our velocity nearly as much as the closer attractor. Its enormous mass compensated for its enormous distance. Think about what this means. For most of the 20th century, cosmologists had been trying to explain a velocity with one gravitational source. When Norma turned out to be smaller than expected, the budget needed filling. Shapley, 650 million light-years away, was filling a significant portion of it. The picture was becoming larger, literally. The gravitational influences shaping our path through the universe were not local. They extended across distances that had previously been considered irrelevant to local dynamics. But the velocity budget was still not complete. The Great Attractor plus Shapley brought the numbers closer. They did not close the gap entirely. And the original mass estimates for the Great Attractor were about to be revised in a way that vindicated many of the early critics. The corrected mass figures for the Great Attractor region came in at roughly 90% less than what had originally been claimed, a factor of 10 off from the initial estimates. This revision was scientifically important in 2 ways. First, it confirmed what the critics had argued. The original numbers were overstated. The Seven Samurai had found a real gravitational flow, but they had initially overestimated the mass required to produce it. Second, and more consequentially for the field, the downward revision meant that the Great Attractor alone definitely could not explain our velocity. This forced researchers to take Shapley's contribution more seriously. It forced acceptance that the local group's velocity was the sum of contributions from multiple large-scale gravitational sources spread across hundreds of millions of light-years, not the product of one enormous nearby structure. The story had shifted from a single answer to a web of answers, and the tools to map that web fully did not yet exist. Building those tools would take 2 scientists working at observatories thousands of miles apart, compiling one of the most ambitious observational datasets in the history of cosmology. What they built would not just clarify our motion. It would give the Milky Way something it had never officially had, an address in the universe. Mapping how galaxies actually move through space requires solving a layered measurement problem. When you observe a distant galaxy, you can measure how fast it is moving away from us. But that recession speed combines 2 things: the expansion of the universe pushing everything apart, and the galaxy's own peculiar velocity, its individual motion driven by local gravity. To isolate the peculiar velocity, you need an independent distance measurement. Know the recession speed and the true distance. Subtract the expected Hubble expansion. What remains is the peculiar velocity, the galaxy's real physical motion through the gravitational landscape. Across thousands of galaxies spread over hundreds of millions of light-years, this is an enormous undertaking. R. Brent Tully at the University of Hawaii and Hélène Courtois at the University of Lyon began building exactly this kind of dataset in the early 2000s. Their project became known as cosmic flows. The goal was the largest, most precise catalog of galaxy distances and peculiar velocities ever assembled. The purpose was to use that catalog to reconstruct the gravitational velocity field of the local universe. The first generation established the methodology. The second generation, Cosmic Flows 2, gathered data on more than 8,000 galaxies and represented a qualitative leap in coverage and precision. Later iterations would push further. Cosmic Flows 3 and Cosmic Flows 4 eventually incorporated tens of thousands of galaxies across a much wider volume of space. The velocity field they were reconstructing is essentially a map of how gravity is organized in the cosmic neighborhood. Where matter clumps together, the velocity field converges toward it. Where matter is sparse, galaxies flow outward into relative voids. The velocity field is a direct readout of the gravitational landscape, like contour lines on a topographic map of invisible terrain. As the atlas took shape, it revealed something unexpected. The flowing patterns in the velocity field were not simply converging on a few isolated attractors. They were organized on a scale far larger than anticipated. The flows traced coherent structures, regions where the motions of thousands of galaxies were correlated, basins where everything drained toward a common gravitational center. Individual galaxy clusters sat inside larger superclusters. Superclusters sat inside enormous gravitational basins. The local universe was structured not as a collection of scattered clumps, but as a nested architecture of flows and attractors operating at multiple scales simultaneously. One feature of that architecture, visible in the cosmic flows, 2 data, was so large and so coherent that it demanded its own name. The result was published in the journal Nature on September 4, 2014. The paper was led by R. Brent Tully. It contained a single central result built from more than 8,000 galaxy peculiar velocities. The Milky Way belongs to a single coherent gravitational structure, 520 million light-years across, containing more than 100,000 galaxies, carrying a total mass of approximately 100 quadrillion times the mass of our Sun. The team named it Laniakea, from Hawaiian words meaning immeasurable heaven. Here's what the paper actually demonstrated. The cosmic flows, 2 velocity data allowed the team to identify gravitational basins in the local universe. A gravitational basin is defined by flow. If the peculiar velocities of all galaxies in a given region ultimately converge toward the same gravitational center, those galaxies belong to the same basin. They are part of the same structure even if they are currently hundreds of millions of light-years apart. The team applied a watershed algorithm to the velocity field, the same kind of mathematical technique used in terrain analysis to define drainage basins in physical landscapes. Every galaxy flows downhill in the gravitational landscape. Trace where they flow, and you define the basin walls. Laniakea emerged as a single basin of enormous scale. The Milky Way sat inside it. The Great Attractor region, specifically the area centered on the Norma cluster, sat near Laniakea's gravitational core. The Shapley supercluster sat beyond the basin's far boundary, outside the defined structure, contributing its gravitational pull from outside. Before Laniakea, the Milky Way's largest named gravitational context was the local group, about 60 galaxies spread across 10 million light-years. Zoom out from there, and we had belonged to something called the Virgo supercluster, a loosely defined collection of galaxy groups. Laniakea swallowed the Virgo supercluster and revealed it to be just one small piece of a vastly larger gravitational basin. 520 million light-years of organized gravitational structure, and we had been living inside it without any awareness of it as a coherent entity. The discovery gave people something concrete. A cosmic address, Milky Way, local group, Laniakea, a hierarchy placing our galaxy inside a structure 500 million light-years wide. But within the scientific community, something else in the data attracted attention that broader coverage largely missed. Laniakea was mapped. The velocity budget was substantially explained. Great Attractor plus Shapley together accounted for most of our 630 kilometers per second of motion. Most, not all. A residual remained, a few tens of kilometers per second, unaccounted for, persistent, showing up no matter how carefully the calculation was run. In cosmology, a few tens of kilometers per second is not noise. It is a signal. Yehuda Hoffman at the Hebrew University of Jerusalem led a team that applied a different analytical approach to the cosmic flows. 2 velocity field. They used a mathematical technique called Wiener filter reconstruction, which uses observed peculiar velocities to infer the full underlying density field, including regions where observational data is sparse or missing. The technique fills in the gravitational picture with the best possible estimate given what is measured. The reconstruction revealed something the standard approach had missed, not a new attractor, not a new massive cluster in some unmapped corner of the sky. What it found pulled attention through its absence. A region of space with significantly less matter than the cosmic average, a void, large and deep, located in a direction roughly opposite to the Great Attractor. If the Great Attractor pulls us toward it from one side, a void on the other side would push us away from that direction, adding to our net velocity. 2 mechanisms, 1 observed motion. The void was pushing nearly as much as the attractor was pulling. Astronomers had been searching for missing mass to explain the residual velocity. The answer was not mass at all. It was the absence of mass. This inverted the mental model that had shaped the field for decades. The attractor story had always been a story about things that pull, heavy objects, dense clusters, massive superclusters. The question had always been, what is massive enough to pull us this hard? That framing assumed the motion was entirely the product of attraction toward high-density regions. It was half right. The other half of our velocity comes from being pushed away from a region that is emptier than average. Hoffman's team published their finding in Nature Astronomy in 2017. They called it the dipole repeller. The result is confirmed science. It demands a change in how we think about gravity's role in the universe. Gravity has always been framed around what is present: mass, density, concentration. But the universe is not uniform. Some regions hold vastly more matter than average. Some hold vastly less. The contrast between them, the gap between the full and the empty, is what actually steers galaxies across billions of light years. We are not just falling toward Shapley, we are also fleeing the void. About half of the Milky Way's cosmic velocity, roughly half the speed at which our galaxy moves through its large-scale environment, is generated by a region containing almost nothing. No single massive attractor, no dramatic concentration of matter, just absence stretched across hundreds of millions of light years. The void does not need to actively push, it just needs to exist. Mass elsewhere creates higher gravitational potential. Matter flows toward it. The regions left behind become gravitational deficits. They push by default, passively, continuously, without a visible source you can point to on any map. This reshaped how cosmologists model our motion through the universe, and it raised a question that had never been asked quite so directly. If a void that size, that far away, contributes that much to our speed through space, what else might we be missing? The answer came faster than expected, and it came not from empty space. It came from behind the wall. Astronomers knew the zone of avoidance was a problem. They worked around it. Infrared telescopes penetrate dust better than optical ones. Radio telescopes better still. By the early 2000s, most astronomers believed the broad strokes of the picture behind the galactic plane were filled in. Perhaps some smaller structures remained undiscovered. But no one expected another Shapley-scale object hiding in the dark. In 2016 and 2017, René Kron-Korteweg at the University of Cape Town decided that level of confidence was not justified. Using the AA Omega multi-fiber spectrograph and the Southern African Large Telescope, her team gathered 4,500 new galaxy redshifts in the zone of avoidance. 4,500 new data points from a region most surveys had treated as effectively blank. What they found stopped the field. A supercluster, a full supercluster comparable in mass to the Shapley supercluster, sitting roughly 800 million light-years away, stretching between 320 and 400 million light-years across. It had been right there behind our own galaxy's disk, and no one had known it existed. They named it the Vela supercluster. The name comes from the constellation Vela in the southern sky. This is a confirmed discovery published in 2017 in the monthly notices of the Royal Astronomical Society. The mass of the Vela supercluster means it exerts gravitational influence on the motion of galaxies in its neighborhood, including potentially our own. How much it contributes to our velocity is still being worked out. Early estimates suggest it may add several dozen kilometers per second to our motion. Every model of how our galaxy moves, every calculation of where we are going and how fast, had been built without accounting for the Vela supercluster. The models were incomplete, the map was wrong, and Vela was not the last surprise hiding behind the galactic plane. Since 2017, a radio array in South Africa called Meerkat has been running hydrogen surveys through the zone of avoidance. Meerkat consists of 64 radio dishes spread across the Karoo Desert, operating together as a single instrument of extraordinary sensitivity. At 21 centimeters wavelength, radio waves pass through the dust of the galactic plane with almost no absorption. The telescope does not need to see around the wall. It sees straight through it. What it sees keeps coming. Hundreds of previously unknown galaxies have been cataloged in just the first years of Meerkat operations, many of them in groupings and filaments, hinting at larger structures waiting to be fully mapped. The surveys are ongoing. Each new data release extends the list rather than completing it. The zone of avoidance was not supposed to contain surprises at this scale anymore. Infrared satellite surveys had been looking through it for decades. The scientific consensus heading into the 2010s was that while some details remained hidden, the major structures were accounted for. Vela, comparable in mass to Shapley, had not been accounted for, and Meerkat is finding that Vela may not be alone. Every new mass discovered behind the zone of avoidance is mass that had not been accounted for in gravitational models, mass that may be contributing to the velocity we thought we mostly understood. We had mapped the forces shaping where the Milky Way goes. We had mapped the part of the sky we could see easily, The rest was still giving up its secrets as recently as 2023. And the zone of avoidance was not the most unsettling blind spot in this story. In 2008, a NASA astrophysicist named Alexander Kashlinsky published a paper that made the scientific community deeply uncomfortable. He did not discover a new supercluster. He did not find a hidden void. He claimed to have detected something far more radical: a motion, a drift shared by thousands of galaxy clusters across billions of light years, all moving coherently in the same direction. He called it dark flow. The claim was specific. Using data from NASA's WMAP satellite, Kashlinsky and his team measured a phenomenon called the kinematic Sunyaev-Zeldovich effect. When photons from the cosmic microwave background pass through the hot gas in a galaxy cluster, they receive a slight energy boost from the electrons in that gas. The size of that boost depends on how fast the cluster is moving and in which direction. By measuring this signal across hundreds, then thousands of clusters, the team built a velocity map. What they found was not random. Thousands of clusters spread across an enormous volume of space, all showing a coherent drift of between 600 and 1,000 kilometers per second in the same general direction. Not local, not caused by anything visible in our observable universe. Coherent motion stretching out to distances of several billion light years. If that signal was real, the implications would require rewriting fundamental aspects of cosmology. Standard models predict that at very large scales, the motions of galaxy clusters should be essentially random. The universe should look the same in all directions far enough out. Coherent bulk motion of that magnitude at that scale is not what the standard framework expects. Kashlinsky's interpretation was direct. The signal pointed to gravitational influence from structures that lie outside the observable universe. Structures beyond the cosmic horizon that can never be directly observed, but that are massive enough to drag thousands of clusters in a single direction across the portion of space we can see. The scientific community did not embrace this claim. The reception was skeptical and persistently so. The methodology was questioned. The statistical approach was challenged. Alternative explanations, from foreground contamination to systematic errors in the WMAP data itself, seemed more plausible to many researchers than gravitational influence from beyond the horizon. But the data would not disappear. Kashlinsky and his collaborators refined their analysis over the following years. They extended it to more clusters. They published follow-up papers in 2010 and 2012. Each time the signal persisted. The direction remained consistent. The amplitude stayed in the same range. The debate was not resolved by argument. It was suspended, awaiting better data. Better data was already in orbit. The European Space Agency's Planck satellite launched in 2009 with the explicit goal of mapping the cosmic microwave background at higher precision than any previous instrument. 30 times more sensitive than WMAP in some frequency channels. 9 frequency bands against WMAP's 5. A map so detailed that when researchers published the first full results in 2013, it reshaped entire fields of cosmology. One of the things Planck was expected to settle was dark flow. The Planck analysis team published their findings across several papers between 2013 and 2016. Their conclusion was direct. They found no statistically significant dark flow signal. The upper limits they placed on any coherent bulk motion fell far below Kashlinsky's claimed 600 to 1,000 kilometers per second. Planck's more precise frequency coverage allowed researchers to better separate foreground dust emission and other contaminants that critics had always suspected were polluting the WMAP measurements. The scientific community broadly accepted Planck's verdict. Dark flow, as Kashlinsky had described it, was most likely a methodological artifact, a contamination problem dressed up as a signal. Kashlinsky disagreed. His response was methodological. He published responses arguing that the two analyses were not directly comparable, that the cluster samples differed, that the filtering choices differed. The teams were not, he argued, running the same test. They were testing different things and comparing results as if they were equivalent. He maintained that the WMAP signal was real, and that Planck's analysis did not cleanly contradict it so much as fail to replicate it using different methods on a different sample. He continued publishing. In subsequent analyses, he and collaborator Fernando Atrio Barandella showed that when the original method is applied to Planck's own data with consistent parameters, a statistically significant dipole signal persists. The signal did not disappear when examined with more sensitive instruments. It changed depending on how those instruments' data were handled. The situation remains uncomfortable for science. Both teams used rigorous methods. Both used real data. They arrived at different answers, and neither side found the specific methodological error in the other's work that would settle the matter definitively. Kashlinsky is now developing an instrument called NBIRD, the Near-Infrared Background and Dipole Experiment, designed for the European Space Agency's Euclid satellite, which launched in 2023. NBIRD would test the dark flow hypothesis through an entirely independent channel, measuring the near-infrared background rather than cluster microwave data. A different signal, a different method, the same underlying question. That test has not yet delivered results. When it does, it will move the needle. What makes this worth extended attention is what it reveals about how science actually operates. Dark flow is science as a sustained, contested, unresolved argument between serious people with serious data. The community has not confirmed dark flow. It has also not proven it wrong. The question remains open in a way that does not make headlines, but does keep cosmologists thinking carefully. And in 2023, a survey of nearly 56,000 galaxies produced a result that reopened the anomalous bulk flow question loudly, and this time from a source no one could easily dismiss. Cosmic Flows 4 was not a radical project by design. It was a catalog, a patient, methodical accumulation of galaxy distance measurements gathered over years by a collaboration of astronomers. The fourth iteration, released in 2023, contained 55,877 galaxy distance measurements, the largest catalog of its kind ever assembled. The intention was straightforward: map galaxy velocities at different distances, compare them to what the standard cosmological model predicts, check for agreement, refine the picture. The picture did not cooperate. At scales of roughly 500 to 650 million light-years, the Cosmic Flows 4 catalog found bulk flows, coherent motions of galaxies moving together through space beyond what the smooth expansion of the universe explains. The measured speed of those flows fell between 380 and 430 kilometers per second. The standard cosmological model, called lambda CDM, which physicists and cosmologists use as their benchmark for understanding the large-scale universe, predicts bulk flows at those distances of roughly 140 kilometers per second. The difference is not small, 3 times larger than predicted at some scales. The probability of finding a bulk flow as large as cosmic flows, 4 reported by chance within a universe governed by lambda CDM, is approximately 1 in 650,000. In scientific notation, that sits between 3 and 6 sigma. A result in that range does not get set aside. The debate is not settled. Researchers have proposed several explanations. Systematic errors in the distance measurements are one candidate. Distance measurements in astronomy are notoriously difficult to make precisely, and at the scales Cosmic Flows 4 was probing, small systematic biases can compound into apparently large signals. Other researchers argue that the peculiar velocity field at these scales is genuinely anomalous and reflects real physics not captured in the standard model. No consensus has formed. What makes this anomaly sit differently than previous ones is the history of the project itself. The Cosmic Flows program has been accumulating data for years. The methodology is well understood. The team published multiple catalog versions before this one. The result did not come from a novel, untested technique. It is the latest and most precise result from a long-running, respected project. And the anomaly grew larger as the sample grew larger. More data made the signal stronger, not weaker. That is not what you want to see if you are hoping for a statistical fluke. Statistical flukes generally shrink as you add more measurements. Real signals hold. In 2026, a prior-free reanalysis of the Cosmic Flows 4 data appeared in the literature. It addressed a potential systematic error called survey anisotropy. The survey is not perfectly uniform across the sky. It covers some regions more densely than others. A non-uniform survey can introduce apparent bulk flow signals that are actually artifacts of the sampling geometry. After corrections for this effect, the bulk flow signal dropped significantly, down to roughly 75 to 80 kilometers per second in some interpretations of the corrected data. That sounds like a resolution. It is not quite one. Even 75 to 80 kilometers per second leaves measurable tension with lambda CDM predictions. Smaller tension that can be addressed with some effort, but tension that does not go to zero. The anomaly shrank. It did not disappear. The pattern worth watching is this. Every time a bulk flow anomaly is analyzed, corrected, and reanalyzed, a residue remains. It never fully reaches zero. It never fully matches what the standard model expects. Each new analysis finds a slightly different answer, but none of those answers lands where lambda CDM would predict. 2 separate measurements of the same physical quantity give 2 different answers. The cosmic microwave background temperature dipole, which measures our motion relative to the ancient radiation filling all of space, gives one speed and one direction. The matter dipole, derived by counting distant galaxies across the sky, and looking for the excess that should appear in our direction of travel, due to Doppler effects and aberration, gives a different answer. Multiple independent surveys of radio galaxies and quasars find a matter dipole roughly twice as large as the temperature dipole. The direction is close, but not identical. The discrepancy sits between 3 and 5 sigma, depending on which survey and which method. It has been found in the NVSS Sky survey data, in the Catwise Quasar Catalog, and in multiple subsequent analyses published between 2020 and 2023. At 3 to 5 sigma, the signal is not ambiguous. One possibility is that the cosmic microwave background dipole has a component that is not purely kinematic, that some fraction of the temperature asymmetry has a different cause, possibly related to an intrinsic asymmetry built into the early universe. If that is true, the temperature dipole does not perfectly encode our motion. Another possibility is that the universe is not perfectly isotropic at the largest scales, that the distribution of matter is genuinely different in different directions, even at distances where the standard framework expects things to smooth out. This would challenge the cosmological principle, the foundational assumption that the universe looks the same in all directions at sufficiently large scales. Both possibilities are serious. Either would require revisions to the standard picture. Neither is resolved. To understand why we move the way we do, it helps to understand the architecture underlying the visible universe. The universe on the largest scales is not filled with galaxies scattered evenly in all directions. It is organized into a network of filaments, long threads of matter hundreds of millions of light years in length, dense with galaxies, connected at intersections called nodes. Between the filaments stretch vast empty regions called voids. The whole structure, visible in numerical simulations and confirmed by galaxy surveys, looks like a three-dimensional web. Each filament connects to others. Each node is a cluster or supercluster where multiple filaments meet. Shapley is a node, one of the most massive nodes in our observable neighborhood. A place where multiple filaments converge and an enormous concentration of mass accumulates. The dipole repeller is a void, a space between the threads where matter is sparse and gravity drains outward in all directions. Laniakea is a basin, a region where galaxy velocities corrected for cosmic expansion flow inward toward a common low point. This structure did not arise randomly. It was seeded by quantum fluctuations in the very early universe, fluctuations so small, they were genuinely quantum mechanical in origin. Those fluctuations became slight overdensities in the distribution of matter. Gravity amplified them over billions of years. Matter fell toward the overdensities, creating filaments. The densest intersections became clusters and superclusters. The regions between them emptied into voids. And most of the matter doing this work is invisible. Dark matter comprises roughly 80 to 85% of the total matter content of galaxy clusters. It does not emit light. It does not interact with light. We cannot see it directly. We infer its existence from its gravitational effects on the matter we can see. In the cosmic web, dark matter forms the actual skeleton. The filaments, the nodes, the overall architecture are primarily dark matter. Ordinary matter, the kind making stars and gas, and planets and everything observable, falls into the gravitational wells carved by dark matter and accumulates there. We are being pulled and pushed by something we cannot see towards something we cannot fully observe, through a structure built primarily from matter we cannot detect directly. The Shapley supercluster pulling us is mostly dark. The dipole repeller void pushing us is defined by the absence of mostly invisible matter. The Vela supercluster behind our galactic plane is a concentration of dark matter, with visible matter tracing its outline. Laniakea itself is a gravitational basin carved by the unseen. Every force steering the Milky Way through space is dominated by something that appears on no light-based map of the universe. That is not a small caveat. It is the central fact of our situation. We are moving through a universe we can see only partially, steered by forces we can only infer, toward a destination defined by structures we are still in the process of discovering. The address of our galaxy in the universe has been revised multiple times in living memory. The Milky Way's largest named gravitational context used to be the Virgo supercluster, roughly 110 million light-years across. Then Laniakea, 520 million light-years across. A study published in 2024 found something that may require another revision. Using updated velocity field data, researchers estimated roughly a 60% probability that Laniakea is not an independent supercluster sitting beside Shapley. Instead, Laniakea may be a subbasin of Shapley itself, a tributary within a larger watershed. A suburb of a city we thought was a separate country. The finding is not confirmed. 60% probability reflects genuine uncertainty. Different analysis methods give different answers depending on how you define the boundaries between gravitational basins at these scales. But if it holds up, the implications are direct. Shapley may not be just a massive neighbor pulling us toward it. It may be the larger structure we already live inside. The attractor we are falling toward may be our own home's organizing center. Each decade, the map gets redrawn. Each revision makes Earth a smaller piece of something larger. This is not an accident. It is a trend. Every instrument we build sees farther. Every survey we run finds more. Every structure we map turns out to sit inside something we had not yet measured. And then there is the structure at the farthest edge of what any survey has ever reached. Everything described so far sits within a few billion light-years of Earth. The Shapley supercluster at 650 million light-years. The dipole repeller at 730 million. The Vela supercluster at 800 million. Laniakea spanning 520 million. These are enormous distances by any human measure. But they are local, fitting inside a small fraction of the observable universe, which stretches nearly 46 billion light-years in every direction. At the largest scales, the standard cosmological model makes a clear prediction. The universe should be smooth and homogeneous. Structures that exist at smaller scales should average out above roughly 1.2 billion light-years. You should not find coherent structures larger than that, because the physics of the early universe, the way matter was distributed after the Big Bang, does not leave room for them. In 2013, a group of researchers found something that challenges this prediction directly. They were mapping gamma-ray bursts, the most energetic explosions in the universe. Brief flashes of radiation so bright they can be detected billions of light-years away. A team led by Attila Horváth at the Konkoly Observatory in Hungary analyzed the statistical clustering of gamma-ray burst positions and found a concentration associated with the constellations Hercules and Corona Borealis. Their estimate for the size of this structure, which they called the Hercules-Corona Borealis Great Wall, was roughly 10 billion light-years across, roughly 10% of the entire diameter of the observable universe. Under the cosmological principle, a structure of that scale should not exist. This result remains debated. The detection method, statistical clustering of gamma-ray burst positions, is not as direct as mapping galaxy redshifts. Gamma-ray bursts are rare and distributed unevenly across time, making a complete and unbiased spatial map difficult to construct. Some researchers question whether the apparent structure reflects a real physical concentration or an artifact of the detection catalog. The Hercules-Corona Borealis Great Wall has not been confirmed to the same standard as Shapley or the dipole repeller. The scientific community considers it a serious candidate structure, not an established fact. But serious is the operative word. A structure at that scale, if real, cannot be explained by current theory. Here is where everything in this story converges on something almost too large to hold clearly in mind. We are a planet orbiting a star in the Milky Way. The Milky Way sits in Laniakea, which may itself sit inside Shapley. Shapley is a node in a cosmic web built mostly from invisible matter. The dipole repeller pushes us from one side while Shapley pulls from the other. The zone of avoidance still hides structures we have not fully cataloged. The cosmic microwave background temperature dipole and the matter dipole disagree by a factor of 2 with no agreed explanation. Bulk flows measured by cosmic flows exceeded standard model predictions by 3 times before corrections, and even after corrections, a residual tension remains. And at the farthest scales ever probed, a structure 10 billion light-years wide challenges the assumption that the universe is smooth. Lambda CDM, the standard cosmological model, has been the foundation of everything we think we know about the universe for roughly 25 years. How galaxies form, how matter clumps, how structure emerges from the chaos of the early universe. It was tested, confirmed, and celebrated. Cosmologists called it the concordance model because so much data pointed to the same answers. But concordance is not unanimity, and lately the cracks are becoming harder to ignore. The bulk flows from cosmic flows, 4 came in at roughly 3 times larger than Lambda CDM predicts. The dipole mismatch between the temperature measurement and the matter count sits between 3 and 5 sigma in multiple independent analyses. The Hercules-Corona Borealis Great Wall, if real, violates the model's predictions about the maximum scale of coherent structures by an order of magnitude. The dark flow signal has never been definitively ruled out. And the convergence depth problem, the fact that every time the reach of peculiar velocity surveys is extended, the sources of our motion appear to retreat farther, suggests the gravitational accounting may not close at any depth we can currently measure. Each of these anomalies considered alone has a reasonable response: measurement error, selection bias, statistical fluctuation. The scientific community is rightly cautious about any single strange result, but multiple independent anomalies, each pointing toward the same general conclusion that the universe is less smooth, less uniform, and less well described at large scales than lambda CDM predicts, that is a different situation. Several cosmologists have said publicly what used to be discussed only in conference hallways. The standard model is not broken, but it may be incomplete. There may be physics operating at the largest scales that the current framework does not account for. This matters directly for the question of what is pulling the Milky Way. Our galaxy's 600 km/s motion was supposed to be explained by lambda CDM working through the Great Attractor, the Shapley concentration, and the dipole repeller void. Known structures, known physics, known mathematics. But if the model is cracking at the edges, the sources of that motion may not be fully known. There is also the fact of where we are going and the guarantee that we will never arrive. In 1998, two independent research teams were measuring the brightness of distant type Ia supernovae. These stellar explosions are consistent enough in their peak luminosity to serve as standard candles across cosmic distances. By comparing how bright they appear against how bright they should be at a given distance, astronomers can reconstruct the expansion history of the universe. Both teams expected to find that expansion was slowing down. Gravity was supposed to be doing what gravity does, pulling matter together and gradually decelerating the outward momentum left over from the Big Bang. Instead, they found the opposite. Expansion was speeding up. The universe is accelerating outward. Something is pushing space itself apart, and that something is winning against gravity on the largest scales. The teams shared a Nobel Prize in 2011. The acceleration is confirmed physics. The name given to whatever is causing this is dark energy. It does not heat anything. It does not radiate. It cannot be detected directly. It is a mathematical placeholder for an observed physical effect. By the best current measurements, dark energy accounts for roughly 68% of the total energy content of the universe. Ordinary matter accounts for about 5%. Dark matter about 27%. Here is what dark energy does to the question of where we are going. The Milky Way is falling toward the Great Attractor region, roughly 150 million light-years away, and beyond it toward the Shapley concentration at 650 million. Our galaxy moves toward them at hundreds of kilometers per second. That motion is real. It is measured. It is not going to stop. But the space between us and those structures is also expanding, and because of dark energy, that expansion is accelerating. The Great Attractor and Shapley are actually moving away from us even as we fall toward them. We are chasing a target that is, in the deepest physical sense, running away. For now, gravity still dominates at these scales. The pull is real enough that we have a genuine peculiar velocity, motion beyond what expansion alone would produce. But at greater distances and over longer timescales, expansion wins. Dark energy operates uniformly across all of space. It does not negotiate with the gravitational attractions of individual superclusters. The mathematical consequence is this: we will never arrive at the Great Attractor. We will never reach Shapley. The fall continues indefinitely, but the destination keeps receding faster than we can close the gap. We are in permanent freefall toward a horizon that the universe guarantees we can never cross. There is something even more unsettling about the long-term geometry of our situation. Laniakea, our supercluster, the structure 520 million light-years across that was revealed by the cosmic flows. Two data in 2014 is not gravitationally bound. This is the distinction that gets lost in almost every popular account of the discovery. A gravitationally bound system, like the Milky Way itself or the local group, will stay together. Gravity holds it through any amount of expansion. But Laniakea is a flow pattern, not a bound structure. It describes where things are currently moving, not a configuration that will persist. Dark energy will take it apart over tens of billions of years. Accelerating expansion will overcome the gentle gravitational tendencies that currently define Laniakea's basin. The outer edges will begin to drift away. The inflow that today characterizes the basin will slow, then reverse in the outermost regions, as expansion outpaces the gravitational gradient. What is now a coherent gravitational watershed will fracture into disconnected islands of locally bound mass. The Milky Way falls toward a center that is itself dissolving. We are passengers in a river that is drying up even as we move downstream. The destination has an expiration date we will never live to witness. This is where the investigation currently stands. We know the speed, roughly 600 kilometers per second relative to the cosmic microwave background reference frame, confirmed by multiple independent methods across decades of observation. We know the direction, toward the constellation Centaurus, toward a concentration of mass roughly 150 million light-years away, and beyond it toward the Shapley concentration at 650 million, steady across progressively better observations spanning 30 years. We know the structure we belong to. 520 million light-years of gravitational watershed containing the equivalent of 100 million billion stars, with our galaxy sliding inward along invisible lines of gravitational force toward a center it will never reach. We know the void at our back, the dipole repeller, an enormous underdense region pushing us forward as surely as any attractor pulls us. We are drawn toward something. We are also expelled from something. Both forces right the path. We know we will never arrive. Dark energy makes it mathematically certain. The fall is permanent. The destination recedes. The free fall continues without end. And we know the model has cracks. Lambda CDM has carried cosmology for 25 years and earned that trust many times over. But the bulk flows are persistently larger than predicted. The dipoles do not fully align. The large-scale structures push against the smoothness the model requires. Every correction leaves a residue. Something remains unaccounted for. There are structures behind the galactic plane that no optical telescope has fully mapped. Radio surveys are finding them now, frequency by frequency. Each new mass discovered behind that dust shifts the gravitational accounting. The picture has blank spaces that are only now being filled in. There are depths beyond current surveys where the convergence problem might finally close, or where it might push the unresolved source of our motion even closer to the horizon, closer to the edge of what any instrument can ever reach. The next generation of catalogs will get there within this decade. The Dark Energy Spectroscopic Instrument Survey, now underway, is the largest test yet. It sits on a telescope at Kitt Peak Observatory in Arizona and began its main survey in 2021. When complete, it will have measured the redshifts of roughly 40 million galaxies and quasars spanning 11 billion years of cosmic history. From those redshifts, peculiar velocities can be extracted. Bulk flows can be mapped to depths and densities that no previous survey approached. The Vera C. Rubin Observatory in Chile, entering its operational phase now, will photograph the entire southern sky repeatedly over 10 years, accumulating a dataset so large its volumes are measured in petabytes. Among its many scientific goals, it will identify hundreds of thousands of type Ia supernovae, the same standard candles that revealed cosmic acceleration in 1998. Each one is a distance measurement. Each distance measurement is an input to the peculiar velocity field. Hundreds of thousands of new data points, where previously there were hundreds. The Euclid satellite, already operational and launched by the European Space Agency in 2023, is mapping the shapes and positions of billions of galaxies across the past 10 billion years of cosmic history. Its weak gravitational lensing maps will reveal the large-scale structure of matter with precision no ground-based survey can match. It will also carry Kashlinsky's N-Bird instrument, testing the dark flow hypothesis through near-infrared measurements entirely independent of any previous method. And Meerkat in South Africa is actively working through the zone of avoidance, cataloging galaxies in the hidden zone and filling in blank patches that have persisted on maps for decades. Within 10 years, data from these instruments will intersect. The bulk flow anomaly detected by cosmic flows, 4 will be tested against a catalog many times larger. The cosmic microwave background dipole tension will face the most complete galaxy distribution map in history. The zone of avoidance will be substantially illuminated. If the anomalies resolve, the bulk flows will shrink toward lambda CDM expectations, and the model will be confirmed at new precision. If they deepen, the universe will look genuinely stranger than the framework allows. One answer confirms, the other breaks something open. Both answers matter, and we will know which one it is sooner than most people realize. The instruments are already running. The surveys are deeper than anything before them. And the anomalies are still there, waiting to be explained or confirmed. We know more about where the Milky Way is going than any human generation before us. We also know that the picture still has gaps, that some of those gaps are behind a wall of dust, some are beyond the reach of current instruments, and at least one may be beyond the reach of any instrument that could ever be built. The investigation is not winding down. The resolution is sharper than it has ever been. The next survey is already collecting. There is another way to understand why this story matters beyond the sheer scale of the numbers. Most of us move through our lives with an intuitive sense of place. We know which city we live in, which country, which continent. We know our address. We know how to situate ourselves in a familiar geography. But almost none of us carry a sense of where we are in the universe. And the reason for that is not just that the scales are too large to feel. It is that the science needed to answer the question was simply not available until very recently. The Great Attractor was identified in 1986. Laniakea was named in 2014. The dipole repeller was confirmed in 2017. The Vela supercluster was discovered in 2017. These are not ancient discoveries that humanity has had centuries to absorb. They are findings from within a single generation's lifetime. The cosmic address we now have for our galaxy is newer than the internet, and it keeps changing. Every decade, better instruments and more complete data revise the picture in the same direction, outward. Our galaxy is revealed to sit inside something larger than we thought, which sits inside something larger still, which may be connected to something we have not yet fully mapped. This is not a sign that the science is unreliable. It is a sign that the science is working. Each revision represents a genuine increase in understanding, a more accurate picture of a structure that was always there, that we were always inside, but that we lacked the tools to see clearly. What makes the current moment particularly interesting is the combination of confirmed science and open questions that coexist in the same picture. On the confirmed side, we move at 600 kilometers per second toward the Shapley region. The Great Attractor is a real gravitational overdensity. The Shapley supercluster is real and massive, and contributes significantly to our velocity. The dipole repeller void is real, and contributes roughly as much as Shapley pulls. Laniakea is a real gravitational basin, 520 million light-years across. The Vela supercluster is real, and was genuinely hidden. Dark energy is real and will prevent us from ever reaching the structures pulling us. These are not hypotheses or speculations. They are confirmed results from multiple independent measurement programs. On the open side, the bulk flow measurements from cosmic flows exceeded standard model predictions significantly and retain unexplained tension even after corrections. The temperature dipole and the matter dipole disagree by a factor of 2 with no consensus explanation. The convergence depth problem has not been resolved, with the source of our motion appearing to retreat as surveys extend deeper. The dark flow signal from Alexander Kashlinsky's work has been neither confirmed nor definitively ruled out. The Hercules Corona Borealis Great Wall, if real, would violate the smoothness prediction of the standard model at its largest scales, and 20% of the sky remains partially obscured by our own galaxy's dust plane. Open questions in science are not a sign of failure. They are the frontier. They are where the next generation of instruments and researchers will direct their attention, and the answers they find will either strengthen the framework we have or reveal something genuinely new about the physics governing the universe at its largest scales. Consider for a moment the character of the anomalies that have accumulated in this field. They share a specific quality. Each one involves the universe appearing slightly more organized, slightly more structured, slightly more directional than the standard model predicts. The bulk flows are too large. The matter dipole is too large. Dark flow, if real, would be far too large and too coherent. The Great Attractor itself was, at first, too large. Structures keep turning out to be more concentrated, more coherent, more directional than a smooth isotropic universe should allow. This may be a coincidence. Multiple independent measurements pointing in the same qualitative direction by chance. Statistical flukes don't typically cluster around the same theme, but they can. Or it may be telling us something about the universe at scales we have only recently begun to probe seriously. That the distribution of mass is less uniform than the standard model predicts. That there are structures, or absences of structures, at scales we have not yet fully mapped, contributing to flows and velocities that the model cannot fully account for. That physics we do not yet understand operates at the boundaries of the observable universe, or beyond them. Both possibilities are worth taking seriously. Neither has been ruled out. The scientific community is in the middle of the most intensive effort ever mounted to map the gravitational landscape of the local universe. The instruments are built, the surveys are running, the data is accumulating. Within the next decade, the picture will be sharper than it has ever been, and we will know whether the anomalies resolve or deepen. There is something worth pausing on in the story of the Great Attractor itself. When the Seven Samurai published their findings in 1986, they were claiming that hundreds of galaxies spread across a region hundreds of millions of light-years wide were all streaming toward the same point. Their colleagues found this implausible because it contradicted what the standard models predicted. Large-scale organization of that kind was supposed to be impossible. The universe was supposed to be too smooth. The Seven Samurai were right about the flow. They were wrong about the mass of the object generating it, significantly wrong, which the critics correctly pointed out. But the core discovery, the coherent streaming motion of hundreds of galaxies, survived every challenge. What the field learned from that episode is that large-scale organized motion is possible in the universe, that the models which predicted it was impossible needed revision, and that getting the direction of an effect right matters even when the magnitude is off. That lesson is relevant to the current anomalies. Cosmic flows. 4 may have overestimated the bulk flow. The prior free reanalysis suggests the magnitude was reduced by corrections, but the residual tension did not go to zero. The direction of the anomaly, toward flows that are larger and more organized than lambda CDM predicts, persisted through the corrections. Dark flow may be smaller than Koszaliński claimed. It may be undetectable at the precision Planck could achieve, but Koszaliński's methodological argument that the two teams were not testing exactly the same thing has not been refuted. The N-Bird instrument will apply a completely independent method, and independent methods are what settled the Great Attractor debate, not arguments about who was right. The cosmic microwave background temperature dipole and the matter dipole may agree once systematic errors in the radio galaxy catalogs are fully understood. But the discrepancy has persisted across multiple independent catalogs, using different surveys with different systematics. The simplest explanation for a measurement that survives multiple independent reproductions with different methods is usually that it is real. The history of this field is a series of moments where a persistent signal was initially attributed to measurement error, then survived successive attempts at correction, and ultimately required a revision of the underlying model. The Great Attractor went from implausible to confirmed. Dark energy went from unexpected to Nobel Prize. The cosmic microwave background itself went from unexplained noise to the most precisely measured radiation field in physics. Not every persistent anomaly leads to a discovery. Some do resolve into improved measurements and better corrections. But the pattern of how this field has worked, where the universe keeps turning out to be more structured and less smooth than expected, gives the current anomalies at least enough credibility to take seriously. The next few years will be informative. The dark energy spectroscopic instrument is accumulating data at a rate that will quadruple the size of existing peculiar velocity catalogs. The Rubin Observatory will add independent distance measurements from supernovae. Euclid will provide gravitational lensing maps of the matter distribution. Meerkat will continue filling in the zone of avoidance. If the standard model is fundamentally correct about large-scale structure, the anomalies will shrink and converge toward its predictions as the data improves. If the anomalies persist or deepen despite larger and more complete surveys, the implication will be that the physics operating at the largest scales is genuinely not fully captured by the current framework. Both outcomes would be scientifically valuable. Confirming the standard model at new levels of precision is a major scientific achievement. Finding genuine deviations from it would open an entirely new chapter in cosmology. What we know right now, at this moment, is that the Milky Way is moving through space at 600 kilometers per second towards structures that include the most massive known concentrations of matter in the local universe, pushed from behind by the largest void in our cosmic neighborhood, inside a gravitational basin that may itself be part of a larger structure, through a cosmic web built mostly from matter that cannot be observed directly, toward a destination that the expansion of the universe mathematically guarantees we will never reach. That is what we know. The open questions about what we do not yet know are, if anything, more interesting. The measurements are becoming more precise. The surveys are becoming more complete. The instruments are better than they have ever been. And the universe, patient and indifferent, continues to reveal itself one data point at a time. The next anomaly is probably already in a dataset somewhere, being checked and rechecked by a team that is about to decide whether to publish a result that does not quite match what the model predicts. The history of this field is a sequence of those moments. The investigation continues. To appreciate the full strangeness of what we have discovered about our cosmic motion, it helps to place it in historical context. For most of human history, the very concept that Earth was moving at all was not just unknown, it was actively disputed. The idea that our planet moved around the sun rather than remaining stationary at the center of everything was considered radical when Copernicus proposed it in the 16th century and remained controversial for generations after. It took centuries of careful observation and mathematics to establish that Earth orbits the sun, that the sun is one of billions of stars in the Milky Way, that the Milky Way is one of hundreds of billions of galaxies in the observable universe, and that all of these structures are moving relative to each other in ways that encode the gravitational history of the cosmos. Each step in that progression required better instruments, better mathematics, and willingness to revise assumptions that seemed obvious and fundamental at the time. The discovery that our galaxy has a peculiar velocity of 600 kilometers per second aimed at a specific point in the sky is the latest step in that long progression. It was made possible by instruments that did not exist until the 20th century, by mathematical techniques developed over decades, and by researchers willing to follow the data wherever it led. The cosmic microwave background, the ancient radiation that provides the reference frame against which our motion is measured, was completely unknown to science until 1965. The DN sigma technique used by the Seven Samurai to measure galaxy distances was developed in the 1980s. The Wiener filter reconstruction method that revealed the dipole repeller was applied to cosmological velocity fields in the 2000s. Each methodological advance opened a new window onto the same underlying physical reality. What has emerged from this accumulated effort is a picture of remarkable complexity. The Milky Way is not simply drifting through empty space. It is embedded in a hierarchical web of gravitational structures, each operating at different scales, each contributing to a velocity that is the sum of all their influences. Nearby structures contribute most. Distant structures contribute less, but are not negligible if they are massive enough, as Shapley demonstrates. Absent structures, regions where matter is sparse, contribute through the asymmetry they create, as the dipole repeller demonstrates. Structures hidden behind our own galaxy's dust plane contribute through motions we can only partially account for, as Vela demonstrates. The convergence depth problem captures the full difficulty of the situation. How far out do you need to look to account for all of the Milky Way's peculiar velocity? The answer has kept moving outward as surveys have improved. It was estimated at 100 to 150 million light-years in the early 1990s. Better data pushed it past the Shapley supercluster at 650 million. Cosmic flows, 4 still found residual tension after accounting for everything within its survey depth. One honest interpretation is that there are still structures we have not fully mapped. The zone of avoidance hides 20% of the sky. The deep universe contains structures we have not catalogued. And at the theoretical limit, there is the cosmic horizon itself, beyond which nothing can ever be observed. If any mass beyond that horizon is contributing gravitationally to our motion, the convergence problem will never be solved through observation alone. Several researchers have noted that the behavior of bulk flow measurements, their persistence at increasing depths, and their consistent direction is consistent with what you would expect from a gravitational source beyond our observational reach. The signal does not weaken the way it should if all the sources are within a measurable sphere. Whether this interpretation is correct, whether there is genuinely something beyond the horizon pulling on us, is a question that may be fundamentally unanswerable by direct observation. This is a genuine limit of science, not a temporary technological gap. The observable universe has a boundary defined not by our instruments, but by the speed of light and the age of the universe. Information from beyond that boundary has not had time to reach us and never will. We can theorize about what lies beyond it. Some inflationary models predict large concentrations of mass energy placed there by the explosive expansion in the universe's first moments. But we cannot test those theories through direct observation. What we can test is whether the signals inside our observable universe are consistent with influence from outside it. If the bulk flow anomalies persist through the next generation of surveys, and if all known internal sources have been properly accounted for, the hypothesis of external influence becomes harder to dismiss, even if it cannot be directly confirmed. This is where the dark flow debate sits, and why it has not simply disappeared despite Planck's null result. Koszaliński's signal has been disputed but not definitively refuted. His new instrument aboard Euclid will apply an independent method to the same question. If N-Bird detects the same coherent flow in the near-infrared background that Koszaliński found in WMAP's microwave data, the case for a genuine physical effect will be significantly stronger. If N-Bird finds nothing, the weight of evidence against dark flow will increase substantially. Either outcome advances understanding. Science does not require the most dramatic interpretation to be correct to make progress. The process of ruling things out carefully and precisely is as valuable as the process of confirming them. There are also puzzles in this story that operate at a more fundamental level than which specific structures are pulling us in which directions. The cosmological principle, the assumption that the universe looks the same in all directions at sufficiently large scales, is the foundation on which the Standard Model is built. If the universe is genuinely isotropic and homogeneous at large enough scales, then on average the matter distribution should be the same in every direction you look. Structures at small scales average out. Voids in filaments and clusters that dominate at millions of light-years become insignificant when you zoom out to billions. The temperature dipole in the cosmic microwave background is supposed to be purely kinematic under this assumption. Our motion creates the asymmetry. The universe itself, corrected for that motion, should look completely uniform. The matter dipole, The asymmetry in the distribution of distant galaxies that should arise from our motion should match the temperature dipole in both direction and magnitude, because both are expressions of the same underlying motion through an isotropic universe. They do not match. The matter dipole is roughly twice as large. This discrepancy has multiple possible explanations, but all of them require some revision to the standard picture. Either the cosmic microwave background temperature dipole has a component that is not kinematic, meaning it reflects some genuine asymmetry in the universe rather than purely our motion through it, or the distribution of distant matter is genuinely anisotropic, meaning the universe actually looks different in different directions at scales where the standard model says it should be smooth, or there are systematic effects in the surveys that have not yet been properly corrected. Any of these would be significant. The third explanation is the most comfortable and is what most researchers currently favor, but it has proven difficult to fully explain the discrepancy through known systematics, which is why the tension persists across multiple independent analyses. The fact that this particular tension sits at the foundation of the standard model, at the level of its core assumption about large-scale isotropy, gives it particular importance. Most anomalies in cosmology are questions about details of structure formation or expansion history. The dipole mismatch is a question about whether the universe is fundamentally symmetric at the largest scales. That is a different category of problem. It is worth being clear about what the standard model has achieved and why these tensions are taken seriously rather than dismissed. Lambda CDM correctly predicted the abundance of light elements produced in the first few minutes after the Big Bang. It correctly predicted the detailed pattern of temperature fluctuations in the cosmic microwave background before those fluctuations were measured at high precision. It correctly predicted the large-scale distribution of galaxies seen in modern surveys. It correctly predicted the acceleration of cosmic expansion that was discovered in 1998. It correctly predicted the baryon acoustic oscillation peak in galaxy distributions that was subsequently measured. These are not trivial accomplishments. They represent genuine predictive success across a wide range of physical phenomena spanning billions of years of cosmic history. A model with that track record earns substantial trust. Anomalies that appear in its predictions should be taken seriously, but so should the enormous body of evidence supporting it. The appropriate scientific posture is neither to dismiss the anomalies as obviously explained by measurement error, nor to declare the model fundamentally broken because of them. It is to investigate carefully, improve measurements, and let the data determine what revisions, if any, are needed. That is exactly what is happening. The anomalies are being investigated carefully. The measurements are being improved. The next generation of surveys will produce data precise enough to either confirm or substantially reduce the tensions, and we will be in a much better position to know which category of problem we are dealing with. This is science working correctly. One of the more remarkable aspects of this particular question, why the Milky Way is moving at 600 kilometers per second in the direction of Shapley, is that it connects the most local and personal experience, the ground beneath our feet, the sky above our heads, the stars we can see on a clear night, to the largest structures in the observable universe, and to open questions at the frontier of fundamental physics. The motion is real. You are part of it right now. Every atom in your body is moving at 1.5 million miles per hour relative to the oldest light in the universe, aimed at something 650 million light-years away that we only fully recognized as a gravitational influence in the last 2 decades. The force pulling you toward it is the same force governing the orbits of planets and the trajectories of galaxies. The void pushing you from behind is one of the largest structures in the local universe and was only confirmed as a significant contributor to our motion in 2017. The reason you cannot feel any of this is the same reason you cannot feel the rotation of Earth. The motion is smooth and everything moves together. But the fact that it cannot be felt does not make it any less real or any less worth understanding. Understanding where we are going, what is pulling us there, and what the limits of our knowledge are on these questions is not just a matter of satisfying scientific curiosity, though it certainly does that. It is also a test of our best current theory of how the universe works, and an increasingly precise probe of whether that theory is complete. The surveys running now will produce answers. Some of those answers will confirm what we already know. Some may challenge assumptions that have been foundational for decades. Either way, the next chapter of this story is being written right now, in observatories across the world and in orbit above it, in datasets being accumulated and analyzed and checked one more time before publication. The investigation is continuing. The universe is patient. The instruments are running. There is a particular quality to the measurements at the heart of this story that deserves extended attention. The cosmic microwave background dipole, the slight temperature asymmetry that tells us we are moving at 600 kilometers per second towards Centaurus, is one of the most precisely measured numbers in all of science. It has been measured repeatedly by independent teams using independent instruments spread across more than 40 years of observational history. The result has been reproduced by the COBE satellite, by WMAP, by Planck, and by ground-based measurements. Every independent measurement agrees on both the speed and the direction. The precision of this measurement is worth appreciating. The temperature of the cosmic microwave background is 2.7255 degrees above absolute zero. The asymmetry caused by our motion is 1 part in 1,000 of that, a temperature difference of roughly 3 millikelvin between the warmer side of the sky and the cooler side. To measure that difference accurately across the entire sky requires instruments capable of detecting temperature variations of millionths of a degree, careful shielding from local sources of radiation, and extensive data processing to separate the cosmological signal from instrumental noise and foreground contamination. The fact that multiple independent instruments with completely different designs and operating in different frequency bands all produce the same measurement is not luck. It is the signature of a real physical signal being measured correctly. This precision has a direct bearing on the open questions. The matter-dipole discrepancy is not small. It sits at 2 to 3 times the size of the temperature dipole. If systematic errors in the galaxy surveys were responsible, those errors would need to be larger than the signal itself, which is possible in principle, but would be a remarkable failure of experimental control across multiple independent surveys using different telescopes and different wavelengths. The persistence of the discrepancy across independent analyses raises the threshold of evidence needed to explain it away. Similarly, the cosmic flows, 4 bulk flow anomaly, even after the prior free reanalysis reduced its magnitude significantly, did not go to zero. The residual tension is smaller than what was initially reported, but it is still a tension. Every successive cosmic flows catalog has found larger bulk flows than the one before it as the survey volume expanded. The anomaly grew as the data grew. That pattern is unusual for a systematic error. Systematic errors tend to be scale independent, or to shrink as sample sizes increase and individual errors average out. A signal that grows with survey volume is either a real large-scale physical effect or a very specific kind of scale-dependent systematic that has not yet been identified. Both possibilities are being investigated. The Dark Energy Spectroscopic Instrument Survey, with its target of 40 million galaxy and quasar redshifts across 11 billion years of cosmic history, will have the statistical power to distinguish between them. The Rubin Observatory's supernova catalog will provide independent distance measurements across a much wider area of sky than previous surveys. If both approaches find the same anomalous bulk flows, the case for a real physical effect becomes very strong. If the anomaly disappears in both, the case for systematic errors is correspondingly strengthened. The key is that the measurements are independent. They use different objects, different techniques, different telescopes, and different wavelength ranges. Agreement between them cannot be attributed to a shared systematic error. There is also the question of what a real large-scale bulk flow would mean theoretically. Lambda CDM is built on the assumption that the matter distribution is random on large scales. The specific pattern of how galaxies cluster and how voids distribute is governed by random quantum fluctuations in the early universe, amplified by gravity over billions of years into the cosmic web we observe. The smoothness and near uniformity of the universe at large scales is a prediction that follows directly from the statistics of those random fluctuations and the physics of how gravity acts on them. If the bulk flows are genuinely 3 times larger than predicted, it means the matter distribution in our cosmic neighborhood is less random and more organized than the standard model allows. There is more large-scale coherence, more directional structure, than random fluctuations amplified by known physics should produce. This could mean several things. It could mean the initial fluctuations in the very early universe were not perfectly random, that some physical process before or during inflation introduced correlations on large scales. It could mean that gravity behaves slightly differently at the largest scales than general relativity, which is the foundation of Lambda CDM predicts. It could mean there are forms of matter or energy that affect structure formation differently than dark energy and dark matter as currently modeled. Or it could mean that our cosmic neighborhood is a statistical outlier, that we happen to live in an unusually structured region of a universe that is on average smooth. Statistical outliers exist. In a universe that is mostly smooth on large scales, there will be some regions where the fluctuations happen to be larger than average. We might live in one, but the probability of a 3 sigma or larger deviation, 1 in 650,000, quantifies how unusual that would be. It is possible. It is the kind of thing that researchers check carefully before attributing a measurement to genuine physics. The dark energy itself, which drives the accelerating expansion of the universe and guarantees we will never reach the Great Attractor, remains one of the most profound mysteries in physics. It accounts for 68% of the total energy content of the universe, and we have essentially no idea what it is. The equations describe its effects precisely: a constant energy density permeating all of space, driving an acceleration of expansion that is measured and confirmed. But what it is physically, what produces it, whether it is truly constant or varies slightly over time, these are all open questions. Some theoretical proposals for the nature of dark energy predict that it might cluster slightly on large scales, similar to how matter clusters. If dark energy is not perfectly smooth, it could affect the growth of structure and the peculiar velocities of galaxies in ways that lambda CDM, which treats dark energy as a perfectly uniform cosmological constant, does not capture. This is an active area of theoretical research, and future surveys will test it with increasing precision. The Euclid satellite's primary scientific mission is precisely to measure the effects of dark energy on the growth of structure across cosmic time. Its galaxy shape measurements, combined with the galaxy redshifts from the Dark Energy Spectroscopic Instrument, will constrain the properties of dark energy more tightly than anything before them. If dark energy has any variation or clustering, those surveys will find evidence for it. All of this connects back to the original question: what is pulling the Milky Way? The answer we have is a lot of things, at different distances, with different contributions, and with some contributions not yet fully mapped, and some potentially beyond the range of any map we can ever make. The Great Attractor region, a broad gravitational basin centered roughly on the Norma cluster, contributes a substantial fraction of our velocity. Shapley, despite its enormous distance, contributes nearly as much through its extraordinary mass. The dipole-repeller void pushes us from behind with force comparable to either attractor's pull. The Vela supercluster, discovered only recently, adds an additional component, and there are structures behind the zone of avoidance, being mapped now by Meerkat, whose full contribution is still being worked out. Whether any mass beyond the observable universe contributes, as Kashlinski's dark flow hypothesis suggests, cannot currently be determined with certainty. The hypothesis has not been confirmed. It has not been ruled out. An independent test is underway. And whether the velocity budget fully closes within the observable universe, whether there is some depth at which all the contributions add up to exactly the measured 600 kilometers per second, is a question whose answer keeps moving outward as surveys improve. This is the frontier of one of the oldest human questions. Where are we? Where are we going? What is out there? The answers we have are better than any previous generation had. The questions we still face are correspondingly harder. The instruments being built right now will answer some of them and reveal new ones. That is the nature of science at its edges. Each answer opens a view onto something further out. The Milky Way moves at 600 kilometers per second towards something we can see only partially, pulled by forces built mostly from invisible matter, pushed by the emptiness behind us, embedded in a structure we only named 10 years ago, falling toward a destination we will mathematically never reach. That is what we know. What we do not yet know is at least as interesting. To close the gap between what we observe and what we can explain, scientists have developed an increasingly sophisticated toolkit of methods that work together in ways that were not possible even 2 decades ago. Consider how peculiar velocities are measured. 3 independent techniques are now widely used, and they draw on completely different physical properties of galaxies. The first is the Tully-Fisher relation, developed in the 1970s. Spiral galaxies rotate, and the speed of that rotation correlates tightly with the galaxy's true luminosity. Measure how fast a spiral galaxy is spinning, determine its true brightness, compare that to its apparent brightness as seen from Earth, and you extract a distance. The method is well calibrated and applicable to large numbers of spiral galaxies spread across the sky. The second is the fundamental plane relation, which generalizes the dn sigma method used by the 7 samurai. Elliptical galaxies have 3 measurable properties: their size, their surface brightness, and their internal velocity dispersion that correlate with each other in a specific mathematical way. If you measure 2 of the 3, you can predict the third, and deviations from the predicted value tell you the galaxy's true distance. This method is independent of the Tully-Fisher relation and applicable to a different class of objects. The third is the type Ia supernova method. When certain binary star systems reach a critical mass threshold, they explode in a characteristic way. The peak brightness of these explosions is well enough standardized that comparing observed brightness to predicted brightness gives a precise distance. Type Ia supernovae are rarer than spiral or elliptical galaxies, but they are visible to much greater distances, allowing peculiar velocity measurements far beyond what the other methods can reach. Each method has different systematic errors. Each has different coverage of the sky. Each is applicable to different populations of objects. When multiple methods agree on the same peculiar velocity for the same galaxy, or the same bulk flow in the same region, the agreement strongly suggests the result is real, rather than a product of any single method's systematic bias. The Rubin Observatory's supernova catalog will dramatically increase the number of type Ia supernovae with measured distances, extending peculiar velocity measurements to much greater depths and covering a much larger fraction of the sky. Combined with the Tully fissure and fundamental plane measurements from other surveys, this will produce a three-dimensional peculiar velocity map of unprecedented completeness and precision. The velocity field this map reveals will be directly comparable to theoretical predictions from lambda CDM models run on supercomputers. Those simulations take the known initial conditions of the early universe and evolve them forward in time according to the laws of physics, producing predictions for how matter should be distributed and moving today. Comparing the observed velocity field to the simulated one is a direct test of whether the physics encoded in the simulations matches the physics of the real universe. If the real universe shows bulk flows 3 times larger than any simulation produces, that is a strong signal that the simulations are missing something. If the real universe's velocity field matches the simulations after observational corrections, the standard model passes a stringent test. The simulations themselves have become increasingly sophisticated. Modern cosmological simulations evolve hundreds of millions of dark matter particles and tens of millions of ordinary matter particles through billions of years of cosmic history, tracking how they form galaxies and clusters and filaments and voids. The largest of these simulations run on dedicated supercomputing facilities and require millions of processing hours. They produce synthetic universes that can be directly compared to observations. The agreement between simulations and observations in many areas, from the large-scale distribution of galaxies to the clustering statistics of galaxy clusters, is one of the strongest pieces of evidence that lambda CDM is fundamentally correct. The disagreements, where they exist, are localized enough that they could plausibly reflect missing physics in the simulations, incomplete observations in the surveys, or both. The bulk flow anomaly is a direct comparison of observed velocities with simulated velocities. If the observations and simulations continue to disagree as both become more precise, the source of the discrepancy will need to be identified. That identification, when it comes, will either reveal a measurement systematic that has been cleverly hiding in the data, or it will reveal something about the physics of the universe that the standard model does not capture. Both outcomes advance understanding. Both are worth the effort. Both are being pursued right now. The particular region of sky toward which we are moving, the Centaurus constellation and the structures behind it, has been one of the most intensively studied regions in extragalactic astronomy for decades. The Great Attractor was identified there. Norma Cluster sits there. The Shapley supercluster lies in that general direction of sky, though farther away. Laniakea's gravitational core is located there. That concentration of attention has produced the most detailed understanding of any comparable volume of the local universe. The three-dimensional structure of matter in that direction, the velocity field threading through it, the mass distribution of individual clusters and their relationships to each other, all of this is mapped in more detail than most other regions of comparable size. What has that detailed mapping revealed? First, that the Great Attractor is not one thing, but a region. A broad gravitational basin containing multiple significant clusters, the Norma cluster being the largest single node, surrounded by a network of smaller concentrations and connecting filaments. Second, that this basin connects to the broader Laniakea structure, defining its gravitational core but not exhausting it. Third, that Shapley, sitting beyond the basin's far boundary, adds a gravitational contribution that flows inward through the same region, creating a compound pull that involves both structures simultaneously. The geometry of this is interesting. We are inside Laniakea, falling toward its core. The core is the Great Attractor region, but beyond the core, still pulling from farther away, is Shapley. We are falling toward a gravitational center that is itself being influenced by a more massive structure still farther out. The flow is not simple. It is a superposition of influences at different scales. And behind us, the dipole-repeller void creates a gravitational deficit that adds to our velocity in the same direction as both attractors. We are simultaneously pulled from ahead and pushed from behind, and both forces point the same way. The alignment is not coincidental. It reflects the underlying topology of the cosmic web in our neighborhood. The Shapley concentration, the Laniakea basin core, and the dipole-repeller void are all part of the same large-scale structure. We happen to be located in a region where the flows from all three converge into a single net velocity. This alignment raises an interesting question about whether our location in the universe is particularly special, unusually dynamic, representative of average conditions, or something else. Without comparing our situation to many other locations, it is hard to say. Cosmological simulations can help here. They produce many regions with different configurations of attractors and voids, and the peculiar velocities of galaxies in those regions follow a distribution. Our measured 600 kilometers per second can be placed within that distribution to ask, how typical is this? The answer from current simulations is that our velocity is somewhat higher than the median, but not dramatically unusual. Roughly 15 to 20% of galaxies in similar environments have comparable peculiar velocities. This suggests we are not in an exceptionally special location. We are simply somewhere in the tail of the distribution, where the combination of pulling and pushing happens to add up to a somewhat above-average net motion. The bulk flow anomaly, if real, would shift that picture. A bulk flow 3 times larger than lambda CDM predicts would mean not just that we happen to have an above-average velocity, but that the entire region of space we live in, hundreds of millions of light-years across, is moving faster than any comparably sized region in any simulation. That would be genuinely anomalous. Not just a location in the tail of a normal distribution, but something outside the range the distribution predicts. Which brings us back to where we are. The data says something. The model says something slightly different. The difference has been measured carefully and found to be robust against a range of systematic corrections, though not against all of them. The next surveys will narrow the remaining uncertainty substantially. We live in an unusual moment in the history of this question. The measurement precision is high enough that real anomalies can be detected. The theoretical framework is well enough developed that the significance of deviations can be calculated precisely. And the instruments needed to test the anomalies at higher precision are either operating or will be within years. Whatever the universe turns out to look like at the scales being probed, the answer will be informative. And whatever picture emerges, we will be moving through it at 600 kilometers per second in the direction of Centaurus, falling towards structures we named only recently, pushed by a void we confirmed only a few years ago, inside a supercluster that has a name only since 2014. The picture is incomplete. It is also the most accurate picture of where we are and where we are going that any generation of humans has ever had. Each survey that runs and each instrument that is built brings the picture into sharper focus. The question is ancient. The tools are new. The answer is still forming. Let us trace the chain of reasoning once more, cleanly, from the most local to the most distant, because the full picture is worth holding together. Earth moves at 67,000 miles per hour around the Sun. This motion has been known and precisely measured since the 17th century. The solar system moves at 500,000 miles per hour around the center of the Milky Way galaxy. This was established through 20th century astronomy. The local group, which includes the Milky Way, Andromeda, and roughly 50 to 60 smaller galaxies, moves at 1.5 million miles per hour relative to the cosmic microwave background. This was first precisely measured in the 1970s using the temperature dipole in the ancient radiation. That final motion, 1.5 million miles per hour, or 630 kilometers per second in the units physicists use, is the number that launched decades of investigation. Where is it coming from? What is generating it? How far out do you have to look before all the sources are accounted for? The Great Attractor, identified by the Seven Samurai in 1986, was the first piece. A broad gravitational overdensity in the direction of Centaurus, hiding almost entirely behind the zone of avoidance, where our own galaxy's dust blocks optical observation. It took X-ray telescopes to see through the dust and find the Norma cluster at the heart of the region. Shapley, sitting 650 million light-years away, was initially considered too distant to matter. It turned out to matter significantly. Its mass, roughly 50 quadrillion solar masses spread across more than 8,000 galaxies, is large enough that at even that distance it contributes gravitational pull comparable to the much closer Great Attractor. The dipole repeller, confirmed in 2017, added a new dimension to the picture. We are not just being pulled toward Shapley, we are also being pushed away from a vast void roughly 700 million light-years in the opposite direction. That push adds roughly half our total velocity, equivalent in magnitude to the pull from Shapley. Two forces, one motion, attraction from ahead, repulsion from behind, both acting in the same direction. Laniakea, named in 2014, gave this motion a structural context. The Milky Way, the Great Attractor region, and 100,000 other galaxies are all part of a single gravitational basin 520 million light-years across. We are flowing toward its core, which is near the Great Attractor region, as part of a coherent large-scale flow that connects hundreds of millions of light-years of cosmic structure. Vela, discovered in 2017, added a structural element we had not known existed, a supercluster comparable in mass to Shapley, hidden behind our own galaxy's dust plane, contributing an additional gravitational influence whose full magnitude is still being worked out. And the question of whether any of this fully explains our motion, whether the velocity budget closes within the observable universe or whether there is more, remains open. Cosmic flows, 4 found bulk flows, larger than the standard model predicts. Independent analyses reduce the magnitude but not to zero. The next generation of surveys will test this further. This progression, from one well-established fact to the next, each building on what came before, each more distant and more difficult to measure, is a good example of how observational science actually advances. You do not start with the hardest question. You start with what is measurable. You build techniques, you improve instruments, you follow the data to wherever it leads. The Seven Samurai did not set out to discover something that would eventually lead to the naming of a supercluster containing 100,000 galaxies. They set out to measure peculiar velocities across a sample of elliptical galaxies. The discovery came from following the measurements. Tully and Courtois did not set out to discover Laniakea. They set out to build the best available catalog of galaxy distances and peculiar velocities. Laniakea emerged from the pattern in the data. Hoffman's team did not set out to discover the dipole repeller. They set out to reconstruct the full 3-dimensional velocity field from the cosmic flows data. The void appeared when they looked at the full picture rather than just the overdense regions. Kron-Korteweg's team did not set out to discover the Vela supercluster. They set out to gather galaxy redshifts in a region that previous surveys had largely left unmapped. The supercluster appeared when they looked where others had not. Each of these discoveries followed from doing the basic work of science, measuring things carefully, building complete catalogs, looking at all the data, not just the parts that confirm existing expectations. The question of where we are going and why we are going there is not one that was handed to scientists from outside. It emerged naturally from the data itself, from the pattern in galaxy velocities that pointed unmistakably towards something in the southern sky, and from the decades of subsequent work to understand what that something is and how far the influence extends. The current state of the question, with confirmed structures explaining most of our motion, several anomalies suggesting the model may be incomplete, and new instruments poised to measure the situation more precisely than ever before, represents science working as it should. The confirmed parts are genuinely confirmed. The open parts are genuinely open. The difference between them is not a matter of preference or interpretation. It is a matter of how much evidence has accumulated, and how well alternative explanations have been tested. We know what we know. We know what we do not yet know. And the next few years of observational astronomy will sharpen the boundary between them considerably. The universe is moving. Everything in it is moving. We are part of that motion, directed towards something specific, for reasons that are mostly understood and partly still being investigated. The investigation has been underway for decades and is accelerating as instruments improve. The answers, when they come, will be more precise than anything available today. That is the situation as it stands. The scientists working on these questions come from dozens of countries and institutions. They collaborate across continents, share data through open archives, and argue at conferences about methodology and interpretation. The disagreements are real, and sometimes sharp. Kashlinsky and the Planck team have been disputing their findings for more than a decade. The cosmic flows researchers and the critics of their bulk flow results have been working through the details of the discrepancy through successive publications. This is not dysfunction. It is the mechanism through which science converges on correct answers. No single researcher can verify everything. The community works by distributing the labor of checking, replicating, and challenging. When a result survives that process, it is genuinely robust. When it does not, the failure is informative too. The cosmic microwave background dipole has survived every check for 40 years. The Great Attractor's existence as a gravitational overdensity has survived every challenge since 1986. Shapley's contribution to our velocity has survived successive independent analyses. The dipole repeller was found by one team, and its contribution was subsequently confirmed by others using the same cosmic flows data. Laniakea has been reproduced using alternative methodologies by independent groups. The bulk flow anomaly from cosmic flows, 4 has survived the first round of systematic corrections, though it was reduced. Whether it survives the second and third rounds, with better data from the Dark Energy Spectroscopic Instrument and the Rubin Observatory, remains to be seen. The dipole mismatch between the temperature measurement and the matter count has survived analyses using multiple independent catalogs with different systematic error profiles. Whether it survives the combination of Euclid's precision galaxy maps and next-generation radio surveys remains to be seen. Dark flow. Kashlinsky's claim that galaxy clusters share a coherent motion pointing towards something beyond the observable horizon has not been confirmed by an independent method. The Planck team's null result sits in the literature. Kashlinsky's methodological critiques of that null result also sit in the literature. The N-Bird instrument will provide a completely independent test. The result will be informative either way. This is where the science is. Not finished, not broken, progressing, as it has always progressed, through the careful accumulation of evidence and the persistent testing of ideas against data. The Milky Way was here a billion years before any life on Earth was sophisticated enough to look up at the night sky and wonder what was there. It will be here, in some form, for billions of years more. The motion we are part of, the gravitational flow toward the Great Attractor and Shapley, and the structures beyond, has been operating for billions of years, and will continue operating for billions more. Even as dark energy slowly decouples the far parts of Laniakea from each other, and the larger structure dissolves. We happen to exist at the moment when the instruments and mathematics to understand this motion have become available. That is the window we are in. The investigations that have produced everything described here are the work of perhaps a few hundred scientists over roughly 50 years. What they have found is extraordinary. What remains to be found is an open question that the next generation of instruments and researchers will answer. The surveys are running. The data is accumulating. The analysis continues. There is one more thing worth noting about the nature of this particular scientific question. Most questions in science involve phenomena that are, in principle, completable. You can finish mapping a protein structure. You can determine the complete genome of a species. You can measure the charge of an electron to arbitrarily high precision given sufficient instrument quality. There is a definite answer, and the question is just how precisely and confidently you can pin it down. The question of what is driving the Milky Way's peculiar velocity has an unusual character. The answer depends on everything massive in the universe, weighted by distance and direction. In principle, even structures on the far side of the observable universe could contribute if they are massive enough and close enough to the horizon. And beyond the observable horizon, there may be structures whose influence crosses into our observable volume, even though we can never observe the structures themselves. This means the velocity budget may never fully close in a way that satisfies all possible skeptics, because there will always be mass distributions farther away than current surveys reach, and eventually beyond the fundamental observational limit. The physics of cosmic expansion means that some fraction of the universe is permanently beyond measurement. What science can do is account for everything within reach, and measure how well that accounting explains the observed motion. If the measured velocity matches the sum of gravitational contributions from known structures within the observable volume, the question is practically answered, even if it remains philosophically open. If the measured velocity persistently exceeds the sum of known contributions, even with complete surveys of the observable volume, that would be evidence for influence from beyond, which could come from extreme large-scale structures near but beyond the horizon. The next decade of surveys will determine which situation we are in. Complete surveys of the observable volume, at the depth and precision the Dark Energy Spectroscopic Instrument, the Rubin Observatory, and Euclid can achieve, combined with Meerkat filling in the zone of avoidance, will produce the most complete gravitational accounting ever attempted. If the numbers close, we will have a complete physical explanation for why we move at 600 kilometers per second towards Centaurus. If they do not close, the residual will be a quantitative constraint on whatever influence might be operating beyond what we can observe. Either outcome is informative. Either outcome advances science. Either outcome is the result of doing the work that needs to be done, building better instruments, taking more data, checking the results more carefully, and following the evidence wherever it leads. That is the situation we are in, and the investigation continues.